So to be predictive, you must add rate of change, understanding, time to failure estimation, and that's a term that actually I created back in 2006. Confidence or probability, not just promises, and decision guidance, not just charts. And that's why I've used time to failure estimation, because predictive got interpreted as an absolute truth. And there, I actually have stories about that.
Exactly. Time to failure estimation focuses on giving a likely window, not a false guarantee. Predictive maintenance should empower confident decisions, not pretend to predict the exact hour. It's about managing uncertainty with probabilities so you can optimize when to intervene rather than scrambling or overreacting.
So let's say I have an instance, and we'll keep it simple. We'll just use mean time between failures. And I have a machine that has a tendency to fail once a particular fault is detected. Let's say I have an insulation resistance degradation, because we've been talking about bearings way too much. And I know that once I detect that, my mean time to failure is going to fall somewhere between 700 hours and 1200 hours on average. Okay, so sometimes a little shorter, sometimes a little later from the point of detection. And I want to know, while it's operating 6,000 hours a year, if I can make it the next 2 weeks, what's the chance of failure in that 2 weeks? And what's a confidence level I can use to give to management?
You'd start by considering the range of 700 to 1200 hours as your distribution. 2 weeks is roughly 336 hours. If you assume a uniform distribution, you could estimate a probability. For example, if 336 hours is about half of your shortest 700-hour window, you might say there's roughly a 50% chance of failure. You'd then communicate that to management, noting it's an estimate based on historical data, and that the confidence level could be refined with more precise statistical modeling.
Exactly. So basically, you could, well, let's say, how does that curve look? And what if somebody asked me how long will it last? And I say, and we come up with a definition that it's now has, we'll decide that the length it's going to last with a good confidence would be when it has 25% resistance to failure.
In that case, you're essentially setting a risk threshold. If you decide that when there's only a 25% chance of lasting further, you're working with the lower end of the distribution. If you know that degradation usually fails by 700 hours on the early side, you calculate where about 75% have failed. That might be around that lower bound. You tell them, at this point, we have a 75% chance it won't last further, offering a cautious, risk-informed decision point.
So you're saying then at that 700-hour point, that would be the 75%?
Exactly. If 700 hours is the earliest common failure point in your range, you could approximate that as where about 75% have already failed. That's when you'd say to management, we're at a point where only about 25% would still make it beyond this. So it's a conservative call to action.
Okay, considering that the reliability formula is a logarithmic approach, a natural log approach, and I say, okay, at what point across this do I have a 50%, or I'm sorry, let's say a 25% chance of survival? Meaning, I'm sorry, let me correct that. I have a 75% chance of survival. At what point? From the base reliability, and not saying it's 100% reliable ahead of time, but from the point that I've detected it, at what point do I have 75% chance?
You'd use the exponential reliability function. Starting from detection, if you want a 75% survival probability, meaning a 25% chance of failure, you'd solve for time. For a system that's degrading, you'd use historical data or a failure rate. In simple terms, you'd say if we know the failure trend, we calculate how far out you go before hitting that 25% failure point. That gives you a realistic planning window.
Okay, and so at that point, when we're taking a look at this, what if we don't have good solid data available? Are there resources elsewhere that are readily available, say standards or other publicly available documentation where people can go and feel reasonably confident that that is going to give them something in the ballpark? And what would that confidence level, or how would that confidence level be affected?
Yes, absolutely. Standards like ISO 13849 for machinery reliability, or IEE guidelines for electric equipment, or even MIL Hadbeek 217, widely used for electronics, offer baseline failure rates for components. These aren't perfect for your exact system, but give you a reasonable starting point. The confidence level depends on how closely your conditions match those assumptions. You treat it as a ballpark estimate. Better than guessing, but still requiring refinement as you gather real data.
So, one of the things we run into in industry right now tends to be along the lines of actually what we dealt with the whole time, but I'm seeing a resurgence of this where condition based maintenance engineers and technicians, or predictive maintenance technicians or engineers, come back and say, you cannot tell somebody how long something's going to last. Therefore, when you detect something, you tell them it's probably going to fail, or you can't tell them, or you can't give them an answer at all. And I've been involved in a few discussions recently where I see that. So they do things like condemn the P to F chart, or even reliability centered maintenance, and say you just kind of spray at the wall and see what happens.
It's understandable why that skepticism exists. People fear false promises, but that's precisely why we emphasize probability, not certainty. The PF curve or RCM aren't about exact timing. They're about managing risk. We're not telling people it'll fail Tuesday at 3 p.m. We're saying there's a growing likelihood in this time frame. So instead of rejecting these tools, we use them to offer informed guidance, giving decision makers a chance to plan rather than leaving them in the dark.